On this playlist, I have already spoken about single reactions in a lot of details, but this video onwards, we are going to talk a bit about multiple reactions. Okay, now these multiple reactions are essentially of two types: either they are parallel or they are series. Okay, or it can be a mixture of both of these types. So our focus over here is on parallel type of reactions. Parallel means it's like, suppose you have a reactant A, it produces R and it also produces S parallelly. Now only one of them is the desired product while the other one is undesired. This is a typical scenario for parallel reactions. Now, the target for finding parallel reactions is first about the product distribution, and then we want to find the reactor size. Okay, when we are talking about only single reactions, we were not worried about this term, product distribution. But now we are worried about product distribution as well as reactor size. Okay, because we want to get more of the desired product than the undesired one. With this goal in mind, let us just outline the general approach, how we generally address such multiple reaction problems. So first of all, we will target to deal with concentrations. Okay, it is much easier to deal with concentrations instead of conversions. So whichever quantities will be given to us for a particular case, we'll try to convert the conversion terms to concentration terms. Okay, and second is to examine the product distribution, and to do this we will omit the time variable, because you will have some rate expression, right? Say dcr dt, dcs dt. So our target will be to omit this dt term. Okay, and maybe we can obtain something like dcr by dcs. Okay, so this expresses the one of the concentration in terms of the other components concentration, that helps us to treat the problems easily in a mathematical manner. Okay, that will be the general approach. Now out of these two requirements that I was talking about, product distribution and reactor size, in a real world problem, our target is to have small reactor size, okay, and maximum desired product. These are our most valid economic considerations when we are designing reactors. But to meet both of these objectives, you will need to do an economic analysis. Okay, without an economic analysis, understanding both of these conflicting concepts is not possible. But as of now, if you want to just proceed without any economic analysis, our main focus will be on the product distribution, that is maximization of the desired product. Okay, so the product distribution is the most controlling factor in case of our multiple reactions, be it parallel, be it series. Now, coming to explaining how we do this general approach with the example that I discussed over here. So, let me just write it down again. A gives R and S, out of which R is the desired product and S is the undesired product. The rate constants are K1 and K2 for these two different reactions. Now the rate equations are given to us as R equals to dCr dt, that is K1 Ca to the power A1, A1 being the order of the reaction. Rs is given as dCs dt equals to K2 Ca to the power A2. Okay, these are the rate equations given to us. Now our general approach was, first we want to use concentration terms instead of conversion terms. So here we already have concentration terms, we do not have to worry much on that. The next thing is to omit this time variable. Okay, so to do that you simply divide RR by RS, and that will give you K1 by K2 Ca to the power A1 minus A2. Okay, and our target is, if we want to maximize the desired product, that is R, then this RR by RS ratio should be as large as possible. Now here the only controlling factor that you can manipulate is Ca, because K1, K2, A1, A2, these are all constants for a specific system at a given set of conditions, given set of temperature conditions. So we can do one thing, we can keep Ca as low as possible throughout the reactor. Okay, or we can keep Ca as high as possible throughout the reactor. Now Ca again, if we want to maintain a low concentration of Ca, then we will use a mixed flow reactor and maintain high conversion, whereas we can keep Ca high by using a plug flow reactor maintaining low conversion. Okay, these are the many combinations in which we can carry out. Now when to choose what? Okay, how to know when we are supposed to keep the reactant concentration high or the reactant concentration low? So for that we are going to use a mathematical analysis. Let's say we have a case where A1 is greater than A2. That means the desired reaction has higher order than the unwanted reaction. Then if you examine this equation, this is the main expression that relates the two rate equations. Okay, so if A1 is greater than A2, then we will like to keep Ca on the higher side. Okay, then there will be a maximization of this ratio. Okay, because we want RR by RS ratio to be large, so we will keep a high reactant concentration. Okay, and for this purpose we will prefer to use a plug flow reactor or a batch flow reactor. Sorry, I shouldn't say batch flow reactor, I should just write batch reactor. Okay, because there is no flow involved, so either a plug flow reactor or a batch reactor, and this will favor the formation of R. Okay, and also since we are keeping the reactant concentration high, we can use the minimum reactor size when we are using the plug flow reactor or batch reactor. If A1 is less than A2, then we will want to keep the Ca low. Okay, a low reactant concentration will help the formation of R, and this will require a large mixed flow reactor. Okay, so these are the two cases. Another case that can be is if A1 is equals to A2. If A1 becomes equal to A2, then RR by RS will become equals to K1 by K2. So now the entire dependency is on the reaction rate. Okay, but we already know that the reaction rate is fixed for a given set of a specific system like this case. So if we want to control the product distribution now, then we have to somehow manipulate the K1 and K2. Here the type of reactor will not matter anymore. So reactor type will not matter in this case. We will like to manipulate the conditions. Okay. Now how we will manipulate the conditions? Okay. So this K1 and K2, these reaction rates, they are very much dependent on the temperature term, because there is a factor called activation energy. Okay, so one way to manipulate is by changing the temperature level. So how will we change the temperature level? Okay, so let us say that the activation energy associated with the desired reaction is E1, and E2 is the activation energy associated with the undesired reaction. I'm writing it in short. Okay, so now if E1 is greater than E2, then we will like to have high temperature, because the higher temperature will favor more formation of the R component. If E1 is less than E2, that means the undesired reaction is occurring at a higher temperature, then we will like to keep the overall temperature low to favor formation of R. Okay, so in this way you can vary K1 and K2 very easily. Another way to create a difference in such systems is using catalyst. Okay, so the catalyst is going to increase or decrease the selectivity, okay, of specific reactions. So if we want to use a catalyst in this case, our target will be to increase the selectivity in accelerating the desired reaction. This will be our general target. Okay, in this way we can qualitatively get an idea about the product distribution for parallel reaction system. Now let's say, so far in this discussion we have considered single reactant. Okay, so for single reactant, qualitatively how do we determine, that is fairly understandable. But what if we have multiple reactants? Okay, so when we are talking about multiple reactants, there are two controlling factors. One is the concentration of feed materials, and the other one is the contacting pattern. So how these feed materials are coming in contact with each other, that also becomes important. So contacting pattern means both can be high, that is you add, let's say you have a reaction like A plus B gives R and also gives S. Okay, so you can have a contacting pattern such that A and B are both having high contact. It means you are adding A and B all at once. That can be one configuration. Another configuration can be both are low. That means slowly adding A and B. Okay. Another can be one high and one low. That means, let's say you have one of the components already present in the vessel in its entire amount, and you are slowly adding the other component. Okay, so that creates a difference in contacting pattern. Now in general, the depending on how many fluids are reacting together and if there is any recycle involved, there are many possibilities of contacting pattern. Okay, so you have to study all possible such configurations when you are actually doing an engineering case study. But in any case, in any of these cases, the use of proper contacting pattern becomes very critical when you have multiple reactants involved for favoring the product distribution. With this, we come to the end of the qualitative discussion about parallel reactions. Thank you.